What to do? What to do? Let's see. All right. We live. We live. We live. Today we are live and it's working. It's working. So luckily there's no load shedding. Just waiting just a couple of minutes. Okay. Let's just open this up. What do you do? What do you do? What do you do, my people? Are we preparing for these exams? Are we winning for these exams? Just wait for a couple of more people to join on the different forms. All right. Just gonna do it like this. All right. I think my audio. Let me just change my mic because I think this mic of mine. Input mic. Then just gonna try to help people out there. Okay, cool. All right. What happened now? What happened? What happened? My video. All right, cool. There you go. Sorted. I see you. I see you. I see someone there on YouTube, someone there on Facebook. How's my audio like? From my side, it looks like everything is okay. Okay. I'm gonna change my video streaming down so that we can have some bandwidth. All right, let's get started. Okay, so today I'm doing a very interesting question. I'm just waiting for this one little thing that's busy pulling my bandwidth here to just finish. All right, cool. Thanks for that sound confirmation. I'm gonna turn the volume a little bit so that we can hear each other nicely. There you go. I thought that my input was a bit low. Okay, cool. Let's get this show started. So the question that we're going to do today is that the A-frame question. So calculating the cable forces for A-frame mounted on a truck. So, I've seen a number of solutions to that question, and a lot of them are, I'm afraid they don't make a lot of sense. So today I'm hoping that I'll present one of the solutions. It's easy to understand and you can easily follow. So I'm just going to share my screen there. So today I decided to go for a presentation instead of a write-up, because a write-up sort of takes a bit of time. Let me kill my thingy there, and then, right, cool. There's no, let me do it this way. Then let's just stop these displays. There you go. So you should see the full presentation now. So this problem, that truck A-frame question coming from it was the first that we've seen. It was in the November 2006 exam, and it was also asked in the June 2017 and recently in the June 2022 exam. So so last year we did like a improved solution to this. Some of the other solutions that we've seen just didn't make sense, and it was not very methodological, right? So I'm hoping that after today you'll be able to solve this type of questions and any other variation in the future. So the question goes as follows. So you've got a truck which is fitted with an A-frame, of which the legs are hinged to the truck at their lower ends and joined together at their upper ends to form an apex to which one end of the cable from the winch is fixed. So a load of 4,000 newtons is suspended from the apex with an overhang of 800 millimeters. Now, each of the legs is 2.5 meters long, and their lower ends are 1.5 meters apart, and you're required to calculate the force in the cable and the force in each of the legs, and this is for 12 marks. So the first thing that you need to note about this problem is that in the June 2022 and the June 2017, they didn't include the schematic here, which is a schematic that was included in the November 2006. So what I can tell you is that it's almost impossible to solve this problem without the schematic, or at the very least being given that cable angle there of 30 degrees. So in the June 2022 exam and the June 2017, they didn't include it, and we did inform Department of Labor that the question itself is problematic and it doesn't allow candidates to actually answer the question. So you're probably asking yourself, then what do I do when I come to the exam and they don't include that? So you don't give up. You make a reasonable assumption. So the reasonable assumption that you will make here is so you're going to have to make that reasonable assumption. So the reasonable assumption being that that angle there is 30 degrees, or whatever reasonable assumption that you can make. Or if let's say you've never seen this question, then you just need to assume the angle, that cable angle over there, in order for you to be able to actually answer this question. Now, the next step there then is, well, okay, so now that you've got that 30 degrees angle, then it will be easier to actually answer this problem. So you remember that from our 6-step process is, number one, we do a schematic. Then after doing a schematic, we put in the data. And then from the data, we do our primary formula, secondary formula, solve for the missing data, and then do our final solution. So for this one, we going to sort of move slightly differently, but we are going to start with the schematic and then, and then do the formulas. But I'll show you how I did this one, and you'll see, I think, at the end why it makes sense to do it this way. So for this problem over here, you will need to understand the 3D equilibrium of rigid bodies. So that's the easiest way to solve this question. If you try to solve it, like we've seen like some other solutions where like it just gets very confusing. But if you solve it using the basics of 3D equilibrium of rigid bodies, you will see right now that it's actually much faster and easier to understand. So the thing about 3D equilibrium of rigid bodies is that we can't use the normal methodology or the normal 6-step process that we preach, because you'll see, because you have to work out the different components step by step until you get to the final answer. So the first step that you do when you're working with rigid bodies is to do a free body diagram. So now if we look at this specific the truck and the A-frame, we will represent this diagram, this what you call A-frame and truck in a 3 Cartesian plane, so namely the X, Y, and Z direction. Okay, so there we've got our neutral point over there. And then moving that direction, we've got the positive y, and that direction positive x, and then that direction positive z. Okay, so we take everything that we know about the different points. So for example, we know that there at the apex, which is point A, is represented by that point there. And then we see that there's our load there going down at 4 kilonewtons. And then we've got the point B over there, and then that point B is that first in a connection from that first leg there, so that's leg AB. Then you've got AC, and then there's that connection there, and there's that connection over there, and then where it connects to the winch, so we've got that as point D, and then I've represented it there as D, and then we've got that angle as 30 degrees connecting from point D to point A. And yeah, so that's the one neutral. So this is overhung. That point A is overhung, is shown over there. So basically what that means is point A is not sitting on that z-axis. So you go up the z-axis, and then it's overhung by that what you call that 800 millimeters or 0.8 meters. Then from there, you've got the distance between B and C, which is that 1.5 meters. So this is our free body diagram. So from this here, we know that we've got a tension force there on AD. We've got a force there, compression force there on AB, and another compression force there on AC. So with that free body diagram that we have over here, we can then start looking at the different positions. So I'm not really going to go into this 3D equilibrium theory. So I do expect that after this, you will go and review that material. So the 3D equilibrium of rigid bodies comes from a lot of the mechanics textbooks, or even if you Google it, you will find a lot of content on this 3D rigid 3D equilibrium of rigid bodies. All right, so the whole approach when dealing with rigid bodies is you want to determine the position vectors for these three 4 points, which is the position A, B, C, and D. Then once you've determined the position vectors, then you can then work out the different what you call vectors that are acting in the cable, in the leg, in that leg as well. And then taking account, obviously, the weight as well. Now, the first thing that I want to determine is that position A over there, right? So position A, as I've explained in a previous slide, is that it's sort of sitting on the Z, and then there's that overhang. So you want to get to that position. So now we're just going to break it down step by step. So let's look at that triangle A, ABC. So if we look at that triangle ABC and then just look at it from a 2D point of view, this is what we have, okay? So we are given that that leg is 2.5 meters long. So that AC is 2.5, AB is 2.5, and the distance between B and C is 1.5. Now, if I look at the center of that, then I'll just take that 1.5 divided by 2, and then it's that then means that that distance is 0.75 meters. Now, I'm making an assumption here, which is not really sort of given in the actual question, which is that this point A, or the apex, is at the midpoint of that B and C. Okay, so it is a reasonable assumption because a lot of A-frames are sort of set up that way. So yeah, so that's I guess a practical and reasonable assumption. Then from there, I want to first remember the reason why I'm doing all of this is I'm trying to find that Z position of A. Okay, so if you can just imagine, I've got this frame sitting like this, and then it's sort of tilting in, right? So that is that overhang part. So you would agree that the minute if it's straight, then it's coming in, then it's sort of sloping down, and then the actual Z position is slightly less than when it would have been just straight, as represented in this 2D. So we use Pythagoras theorem to work out that first part, which is that that point, that distance there, which I'm calling Q1. And from Pythagoras, we take the hypotenuse squared minus that section squared, and then all square root, and then that works out there. So, but this is not the Z position of point A. So what we need to do is to account for that overhang over there. So if you look at it on the side, so if you can just imagine this here on this, like just cutting it through and looking at from the side. So then you've got position A, and then that 2.38 is basically that hypotenuse over there. Then the overhang is that 0.8 meters, all right, or 800 millimeters. So I'm just representing everything as meters. And then we've got that from Pythagoras, that the Q2, or that distance, or the position of A in terms of from the Z direction, is 2.24 meters. Again, this is basic Pythagoras theorem. Now, from here, you can see that the big thing that I wanted to work out was that position of point A from a Z direction point of view, of which I've sorted out. The next one that I need to sort out is that position vector, sorry, that point there, not position vector, that point, that position D over there. So now to sort out that one, okay, so there, I'm just saying that that's the Z position. To sort that position D, again, just imagine that triangle over there. So there is that big triangle over there. So from the information that we have, we know that that point is overhung. So if it's overhung, then you've got that overhung point of it over there, and that we've worked out as 2.38 meters. And we've worked out also that straight section there is 2.24 meters, and we've worked out that as also this is given as 0.8 meters. Now, this part here, we just look at that big triangle at an angle of 30 degrees. Then we just use the triangle laws. So that's opposite over adjacent, right? So that's 10 of 30 degrees. So if you look at it, so it will be 2.24 over the x that we're trying to work out, and then that will be 30 degrees. So if we take the x the other side, and then therefore it's that 2.24 divided by the 10 of 30 degrees, and that works out to 3.88 meters. Now, we know that that's 0.8 meters, therefore we can find that position there as 3.08. So it's that 3.88 minus that 0.8, and it gives us that position D. So we now have the positions for the different points in our free body diagram. So let's do our locations of interest in, relative to our reference axis, which is that axis over there. Now, if we look at point A, to get to point A, I'm traveling 0.8 meters in the X, and then I'm traveling 2.24 meters in the Z direction, right? And that's how I get to that point. So you would agree that I'm not moving in any direction in the Y direction, and therefore, if I represent point A in terms of the X, Y, and Z coordinates, then it's 0.8 in the X, 0 in the Y, 2.24 in the X. Sorry, in the Z, right? Right. So this IJK, again, it's basic applied mathematics and basic rigid theory. So if you don't know this representation, then it will be very important to review that theory. Now, if we look at point B, so from the neutral point, I'm just moving in the Y direction, positive 0.75 meters. So remember, BC is 1.5 meters, and I'm saying, well, it's reasonable to assume that this is acting at a midpoint, because that's how usually these A-frames are set up. And then on the C, I'm just moving in the negative Y. So as you can see there with the orange, so that's negative 0.75 J, right? And then I'm not moving in the X, and then I'm not moving in the Z. Then we look at that point D, and then point D is negative 3.08, right? So again, I'm not moving in the Z, nor am I moving in the Y. All right, so now I've got the positions in 3D for the different points over here. Okay, so now we can start working out our position vectors. Now the position vectors will be that vector. So if we look at that point A, there's the vector that's over there in AB, that vector in AC, and that vector in AD. Okay, so the vector, the position vector AB will be that 0. So I'm going to look at the X, the Y, and the Z. So it's that the BX minus the BX minus the 0.8 or the AX position. And then I'm going to do it for the Y, do it for the Z, and then that's that over there. And then at the end, I've got that position vector RA. Then I can also do the same for position vector RAC, and then do the same thing for AD. Right. So at the end, these are my position vectors for RAB, RAC, and RAD. So then from there, I want to represent the position vectors as unit vectors. And the reason for that is I want to work on the same sort of units, and so that when I multiply by my forces, then I've got everything sort of aligned properly. Okay, so I go on, then I calculate the magnitude of these three vectors. So again, calculating the magnitude, this is the basics of applied mathematics. So there's the magnitude for RAB, RAC, and RAD. Then from there, I take the position vector, I divide it by its respective magnitude to get the unit vectors. So there, I'm just doing that division. This slide is, okay, there you go. So there is just mathematics, right? Pull out your calculator and you will find that these are your unit vectors. So from here on, remember that the whole point of this question is to try and calculate the tension in that rope over there, given the force there of 4,000 newtons, and you need to calculate the force on those legs over there. So what we can do now is we can now express each of the force in Cartesian form by multiplying the magnitude of the force by the unit vector. All right. So we know here there will be a force. Let's start with AB. There's going to be a compression force FAB there. So I just multiply the unit vector by that FAB, and then for AC I do the same thing. I just multiply it by the force AC, and then for AD, same story. I just multiply it by force, the tension force there, FAD. Now we know that there's that one force that's going there, which is the load. Then that load is just acting on the Z direction, in the negative Z direction, and that's where we get that 4,000 newtons. Now, don't get confused by this K over there. So this K, remember, we've been representing the Z component as K. So this is not 4,000 kilonewtons. So it's just the 4,000 K, or the Z position. Okay, so don't get confused by that one. So this force here is only acting in the Z direction. So then from there on, we can take the sum of the forces in the X, the sum of the forces in the Y and in the Z direction. So again, from basic theory, if I just go back one slide, there. So from there, from rigid bodies theory, we know that the sum in the X direction, the sum of the forces in the X must be 0, the sum of the forces in the Y must be 0, and the sum of the forces in the Z must be 0. So that is the basic rigid body theory. Okay, so all I'm doing here is I'm just summing all the forces in the X and then equating to 0. The forces in the Y must be equal to 0. So you'll see that now that will be my first equation 1. And then from here, this works out to saying, well, force AB is equals to force AC. And by just looking at this arrangement, you would have gotten to that conclusion to say, well, AB will be equal to AC if this thing is sitting at like dead center and the two legs are taking the load equally or divided by 2. All right, so this mathematics that we've done here has proven like that the basics of just looking at that schematic. So we know that we are sort of in the right direction so far. Then we look at the sum in the sum of the forces in the Z direction, that will equal to 0. And then from this one, I'm just going to solve for FAD, and then I'm going to call that equation 3. So the reason for that is I just want to substitute everything back to equation 1, where the only unknown variable will be FAB. So as you can see over there, the only unknown there is FAB, which is that compression force there on that leg. So doing the mathematics, I can find that FAB is negative 2,792.92 newtons. Okay. Then up next, then I can calculate, well, I know that FAB is equal to FAC. So that leg there is also then negative 2,792.94 newtons. Then I can solve for that tension there, and that works out to 2,054.58 newtons. Right. So the question was asking us the cable force and the force on each of the legs, and we are sorted. So the force on the cable is just that FAD, that force AD, and that on the leg is that force AB. I think that's just a typo. So it's that force AB and that force AC over there, which is that 2,992.94 newtons. All right. And then, yeah, so, and then that's the long and short of answering this question. So I think, like, as I said, like some of the solutions that we've seen is they try to reason the different forces, and doing it this way is the fastest way you can solve this problem. And even and the other thing is that in the future, when they ask like similar questions, where it's about rigid bodies, then you know that you just apply the basic theory, and you can answer any static problem in upcoming exams. So this was one of the I guess surprise questions in the June 2022 exam, and it was an easy 12 marks if you just followed this theory. So in past exams, they've asked a different variation of rigid body questions or static questions. Where, for example, there's the cantilever one where they're not saying, well, it's an A-frame, but then they give it to you as like a string connected to a wall, and then there's a cantilever, and then there's a load going down. So even for that one, to calculate the tension and the reaction forces, if you use this basic approach that I've just shown you, you can answer any other question. I hope that was helpful. Let's see if there's any questions. Right, so there's one question. Is this linear regression? No, it's not linear regression. It's a question from the GCC Factories Plant Engineering exam, which basically was requiring the calculation of forces from an A-frame mounted on a truck. Right. So yeah, I think that's the long and short of that. Is there any question from the people who are online? So yeah. So look, if you, I will include a basic, what can I say, like a simplified or a faster solution to this on the YouTube channel. And if you are interested in our upcoming bootcamp, we will be looking at more of these type of questions and then unpacking it much further. I've just shared a link there for our upcoming online bootcamps. So these are for people who are planning to write the GCC Factories exams. So yeah, if you're planning to write the GCC Factories exams, yeah, be sure to join our bootcamp, and yeah, you will see the benefits of it as I'm demonstrating over here. So if there's no other question, I've shared the link to the bootcamp. If there's no any other question, yeah, so I'd just like to thank everyone who managed to, join this lunch hour practice session. So again, we're doing these lunch hour practice sessions as a way of motivating and yeah, trying to make sure that you are up to speed and you are getting motivated and to keep studying for your GCC Factories exams. So if you need anything, I'm just going to share our email address there. It's info@palucraft.com. Palucraft.com. If you've got any other questions that you might have and you are maybe not comfortable asking in a live stream. All right, with that said, thank you very much. I'll see you in the next live stream.